All right, so today's notes are just going to take a closer look at experimental design and some of the things we have to consider. Again, prior to this, we were mostly focusing on like sampling and surveying, and now we're shifting to experiments. And experiments are really important because they allow us to establish causation. And again, the big difference between kind of like an observational study or a survey and an experiment is that in an experiment, we're applying some sort of treatment to our subjects, all right, and then kind of measuring the difference that that treatment makes in our response variables. All right, so principles of experimental design, all right. One very important principle is random assignment, all right, which is saying that the experimental units also known usually as subjects when we're talking about humans, are assigned to their groups at random using some sort of chance process. All right, so why do we do this? All right, why is random assignment important? All right, it's one of the best ways we have to create two groups that are as similar as possible. All right, it doesn't eliminate lurking or confounding variables, but it tries to balance them out between the groups by giving everyone an equal opportunity to end up in either group. All right, so this is kind of a bedrock of experimental design, is that you have random assignment. And again, I'm just going to put some notes here. Best way to create two groups as similar as possible. Because again, your hope is that your two groups are pretty much identical, and the only thing that changes is the treatment. All right, so if the only thing between the two groups that's different is the treatment, it's much easier to establish whether the treatment is effective or not. And then I'm going to say doesn't eliminate confounding variables, but tries to spread them out across the groups. Spread out, I'm going to say their impact across the groups. All right, that way if there is some trait that's influencing it, the effectiveness of a treatment, you're hoping that that trait gets balanced between the groups by randomly assigning it so that they don't accidentally all end up in one group or accidentally end up in another group because of some decision you've made. Kind of a connected or related thing to the random assignment is the idea of a completely randomized design. All right, and this is just sort of taking it to the extreme where the treatments are assigned to all the experimental units completely by chance. So why is this different, or how is this different? We do not force equal group sizes. So let's say I've got 100 people and you either have treatment A or B. I'm not going to be like, oh, I'm going to get 50 with treatment A and 50 with treatment B. What I'm going to do is I'm going to flip the coin for every person, and heads is treatment A and tails is treatment B. So it might end up pretty close to 50-50, but there's no requirement that it ends up with 50-50. If I flip 55 heads, then I'm going to have 55 people in the A group, and I'm only going to have 45 people in the B group. If I flip 62 tails, I'm going to have 38 people in the A group and 62 people in the B group. But completely randomized design means I'm not forcing those groups to be equal. All right, so why is randomized assignment important to produce meaningful results? Again, it helps avoid bias in the assignment process. Assignment process, and reduces, and this is the big part that's important, the chances of systematic differences between the groups. Right? And that's going back to this idea of the best way to create two groups as similar as possible. By randomly assigning, we're hoping there are no systematic differences between the groups where, one trait only ends up in group A and another trait only ends up in group B. By randomly assigning it, everybody has an equal chance of ending up in either group. And hopefully there's no differences that sort of pervade that. And the two groups are as similar as possible so that we can do our comparisons. All right, so a lot of this other stuff you probably have heard before in your science classes and things like that. I mean, you probably heard about this in your science class, but we are going to go over them just to make sure that we're clear on the definitions, because let's be honest, not everybody remembers everything from every class they've ever taken. All right, so control group is a comparison group that receives no treatments. It acts as the baseline for comparison. All right, so obviously right now, I mean, the studies that everybody is talking about are the COVID vaccine studies. They gather all their participants, they give everybody a shot, but some of those shots have the vaccine in it, and some of them have, I don't know actually what they're using in the ones that don't have the vaccine in it, but something that doesn't do anything. And that shot that doesn't do anything is your control group. You're seeing, do people that got the fake shot get COVID more than the people that got the actual vaccination? And we'll talk about why they give the fake shot in a little bit. But that's the idea of the control group, is that it's your baseline for comparison. All right. And there's also this idea in studies of replication, which is using a big enough sample so results are not based on chance. Otherwise can be difficult to verify results. All right, so this is getting a little ahead of where we are now, but we're going to see eventually that when you're doing these experiments, you use this technique called hypothesis testing. And when you hypothesis test, there's always a chance of error. There's always a chance of mistakes. But the larger your sample, the less chance that has of happening, which means that when people replicate your experiment and when people try it again, they're more likely to get results that are in line with you. All right. The smaller your sample, the more your results can fluctuate and vary up and down, which makes it harder for people to replicate your results and then confirm your findings or disprove your findings, as the case may be. But basically, the idea is that the more people you're able to, include in your experiment, the more reliability you can have in your results. All right, so is it possible to do a good experiment without a control group? Generally, the answer would be no, though there are comparative studies that don't involve a control. So it's a different type of study where you're not looking to see, like, does this treatment have an effect? You're just comparing two different things and saying, all right, I want to know what happens with this one versus this one. And there might not be a control in that type of situation, but for the most part, a good experiment requires to have some sort of control to be able to compare the results with. All right. So when we are describing an experiment, when we are talking about how we want an experiment to look, these are the things that we want to be speaking about. We want to be speaking about what's our control, how are we using random assignment, how are we worrying about this issue of replication and sort of reliability. So when talking about the control, you want to be very specific in explaining the experiment. So we control for as many lurking variables as possible. This way, only systematic differences between the treatment groups, differences between treatment groups is the actual treatment administered. All right, so again, that's creating two groups that are as similar as possible so that truly the only difference between them is the treatment that we're providing. All right. Random assignment would be the use of impersonal chance to assign experimental units to treatment groups to create roughly equivalent groups of experimental units by balancing the effect of lurking variables that aren't controlled on the treatment groups. All right, so that was everything we just talked about on the front page there. And then replication, treatment groups should contain enough individuals so that any differences in the effects of the treatments can be distinguished from the chance differences between groups. All right, again, there's always going to be random fluctuation, but the larger your groups, the less likely those random fluctuations are going to influence or flip your results in one direction or another. All right, so does caffeine affect pulse rate? Many students regularly consume caffeine to help them stay alert. Thus, it seems plausible that taking caffeine might increase an individual's pulse rate. Is this true? One way to investigate this is to have volunteers measure their pulse rate. Unfortunately, even if every student's pulse rate went up, we couldn't attribute the increase to caffeine. Perhaps the excitement of being in an experiment made their pulse rates increases. Perhaps it was the sugar in the cola and not the caffeine. In other words, there are many variables that are potentially confounding with taking caffeine. Explain how to use all three principles of experimental design in the caffeine experiment. All right, so again, considering everything that we want to do here, so in terms of the control, all right, if we're worried about the sugar or just participating in the experiment having an effect, what we could do is we could create a control group where they drink caffeine-free cola. All right, so they're still drinking something. It still has sugar. They're doing everything that the other group is doing, and compare them to a treatment group that uses caffeinated. All right. So we've got our control group using caffeine-free cola. We've got our treatment group using caffeinated cola. All right. Everything is the same, only one of the drinks has caffeine in it. The other drink doesn't have caffeine in it. All right. Random assignment. Again, we don't want to just assign the first 10 people to one group, assign the next 10 people to the other group, because what if the first 10 people are people that drink coffee in the morning, so they're there early and they've already got caffeine in their system and something else is going on, right? We want to try to balance as many, outside factors as possible. So we would generate random numbers to divide the subjects equally between two groups. All right. And then replication, we're just going to write try to get as many subjects as the study's budget allows. All right. So again, thinking about a real world setting, there are limits. You don't have unlimited money, but within the budget that you have, trying to get as many subjects as possible to eliminate the influence of random fluctuation corrupting your results one way or another. All right, so let's take a look at another one here. Dueling diets. A health organization wants to know if low carbs or low fat diet is more effective for long-term weight loss. The organization decides to conduct an experiment to compare these two diet plans with a control group that is only provided with a brochure about healthy eating. 90 volunteers agree to participate in the study for 1 year. Outline a completely randomized design for this experiment. Explain how each of the 3 principles of experimental design are utilized. All right, so notice that it says completely randomized design. All right, and that was our second definition on the first page here, but it's the one where we're not forcing equal group sizes. All right, every subject's assignment to a treatment is totally random. So what we do there, if we wanted to outline how that would work, all right, is we could generate random numbers between 1 and 3 for all 90 participants or for all 90 subjects. All right. And then once we've generated those numbers, anybody with a 1 would end up in the control group. Anybody with a 2 would end up in the low carb group. And anyone with a 3 would end up in the low fat group. All right, so we didn't say, oh, we're getting 30 in this, 30 in this, 30 in this. We just said, all right, for every person, we're going to generate a random number, and some will end up in control, some end up in low carb, some end up in low fat. And again, it's going to work out to about 30, 30, 30, but it won't likely be exactly that, but it'll be close, and we'll have ensured that we had no influence in selecting who ended up in which group. All right, if your sample is large enough, those slight differences between the groups aren't really going to make much of a difference anyways. I mean, slight differences in the sizes of the group. All right. All right, so how do we deal with having a control in this group? All right, so the brochure group served as a baseline and made everyone feel like they were part of an experiment. All right, so that way everybody felt like they were part of the experiment. So if just being part of an experiment were to change your behavior, we're trying to make that control group as similar as possible. All right. Random assignment. So again, we generated random numbers to try to create 3 groups as similar as possible. And then again, we had 90 subjects to try and balance out random fluctuations. All right, so again, thinking about all 3 of those aspects when you're designing an experiment. How many people do you need to talk to? And again, later in the course, we'll actually see how you calculate some of these values, like how many people you do actually need to talk to. How are you kind of dividing them up to create groups that are as similar as possible? And then what are you using as sort of a control situation? All right, continuing on, homesick. A counselor at a sleepaway camp came up with a cure for homesickness. When a camper complained about being homesick, she would give the campers a special pill, and most of the time, the campers said they felt better. When her boss found out she was giving the camper pills, the counselor was in danger of losing her job. Obviously, you can't just give kids pills. That's horrible. Until she explained that she was tricking the kids and giving them a small piece of candy. Okay, so there's one story. Here's a second story. 100 volunteers were part of a study to see if a new drug would relieve signs of depression based on participants' self-ratings. The experiment was explained to all participants, and about half were randomly selected to take the new drug, while the others did not. Both groups were evaluated later to compare the change in self-rating scales. This study found that the drug worked. All right, what do these 2 situations have in common? How could this be a problem in the depression experiment? All right. So what do they have in common? In both cases, subjects were taking a pill and said they felt better. So the question was it the pill or was it just because they took something? All right, so here we saw an example of campers taking a pill inside of quotes and they felt better. Here we saw an example of people taking an actual pill and they said they felt better. All right, but if people could feel better taking a piece of candy, how do we know that the actual drug was any more effective than an actual piece of candy? All right, and all of this is going to be highlighting what we call the placebo effect, and we're going to talk about that a little more as soon as we flip the page. But this idea of the act of taking something, the act of doing anything will often make somebody feel better. The mental, rush from being like, okay, I took something, I should start feeling better. Right? The idea that you think you should start feeling better is likely to actually make you feel better. Right? There's a lot of evidence in the brain's role in recovery and how you perceive pain and how you perceive your experiences. It doesn't say that it can like miraculously heal you. If there's an underlying issue, that issue is still there. But your brain can affect sometimes how you perceive that and can affect the speed at which you recover and so on and so forth. All right, so this is all hitting kind of on the placebo effect. All right, so what is our definition going to be for a placebo effect? All right, it is a response to a dummy treatment. All right, it is this notion that if people are taking something, they feel better, even if that something has no real impact. Even if it's just a piece of candy, you're going to say you felt better because you did something. It's like giving little kids a Band-Aid, right? Half the time the Band-Aid doesn't do anything, but they feel better because now they've got a Band-Aid and it makes them feel better about their boo-boo, if you will. All right, so that's why when we're doing these experiments, we usually have to give a fake treatment so that we're actually measuring the effectiveness of the drug or the treatment as opposed to just the fact that somebody got any old treatment. All right, so a placebo is the actual dummy treatment, i.e. some sort of sugar pill, saline solution, etc. But basically something that's going to have no real effect, but it makes them feel like they're getting a shot, or it makes them feel like they're getting an IV, or it makes them feel like they're getting, a pill of some sort, so that we can kind of, account for that mental component and focus on the actual, treatment or drugs or vaccine or what have you. Now, when we set up these experiments, it's important that we have these blindings in effect. All right, so we've got single blinding and we've got double blinding. What's the difference? All right, so blinding is when the individuals participating in a study do not know, if they are receiving a placebo or a treatment. All right, so when the individuals participating in a study do not know what they're receiving. All right, and the reason we do this is placebo effect goes away if people know what group they're in. All right, now you might be saying, well, if it goes away when they know what group they're in, why don't you just tell them? Well, let's think about that for a second. All right, so if you tell somebody, all right, here's your sugar pill, it's not going to do anything. And then you tell the other person, all right, here's your real medicine, it is going to do something. All right, the person that got the real medicine is going to be like, oh, great, I got the real medicine, I'm going to be better. The person that's like got the sugar pill is going to be like, oh, crap, I got the sugar pill, I'm not going to feel better. So it's not the actual act of taking a pill, it's the belief that you're getting the medicine that can sometimes cause, the they can cause you to think there's an improvement when there's actually not, or to think that a drug is doing something when it's actually not. All right, so blinding is when the individuals participating in a study do not know if they are receiving a placebo or not, so that we can sort of control for, that boost that you get just because you took something or because you took a drug. All right, now how is that different from double blinding? Double blinding is when neither or neither the participants nor the researchers interacting with the participants knows who is receiving the placebo. Yeah, who is receiving the placebo versus the actual treatment. All right, so it's not that nobody knows who's receiving what. It's that the researchers that are interacting with the public or with the participants don't know. Because the worry is if the person interacting with the participant knows whether it's the real treatment or not, they might subtly give away hints that the person can pick up on. And when they're picking up on those, it could ruin this whole placebo thing that we were just talking about, where the people that got the fake treatment were able to pick up on it from the researchers. So they were like, oh, I got the fake treatment. This isn't going to do anything. The people that were getting the actual treatment were able to figure that out because of the facial expressions of the researchers. They are excited that they're getting the actual treatment and they think they're feeling better, even if the treatment's not doing anything. All right, so double blinding gets around that by making sure the researchers interacting with the participant doesn't know. So again, let's go back to this vaccine trial. You go and you say, I want to be part of this trial. The person that's giving you the shot has no idea whether they're giving you the vaccine or whether they're giving you a fake shot that doesn't do anything. All right, all they're doing, a researcher gives them, the equipment, or they pick up the equipment. They probably don't even interact with somebody. They're like, all right, here's your shipment. They get the shipment. They administer the shots. They themselves don't know what it was. Somebody observing it knows what it was, but there's that layer of removal so that the participants can't pick up on it, so that your results aren't contaminated by this whole placebo effect problem. All right, last but not least, when we talk about experiments, you're going to hear the word statistically significant a lot. And that means that the observed effects, or the observed effect, is so large it would rarely occur by chance. All right. So basically, big enough so that you don't have to worry about coming to the wrong conclusion because of random fluctuations. All right, so let's tie this back to vaccines one more time. All right, so you've got your group that gets vaccinated. You've got your group that gets the fake shot. What they then do is they send those people out into the world and see who gets COVID, who doesn't get COVID. If the vaccinated group doesn't get COVID and the fake vaccinated group gets COVID, then you've got a pretty good idea that your vaccine works. But it's possible there could just be some random fluctuation there. maybe the group that got vaccinated just didn't come into contact with the virus. And maybe the group that got the fake vaccine came in contact with the virus all the time. There could be things that could subtly affect that. Statistically significant says the observed effect was so large that it's unlikely that it's a result of those random fluctuations. For example, the Pfizer and the Moderna were both shown to be 95% effective. All right, the impact there was so large that, yeah, you can never totally rule out random fluctuations. Maybe everybody that got the actual vaccine just never came in contact with the virus. Pretty unlikely. What's more likely is that the vaccine actually made a difference and was effective. So when the effect is so large that it would rarely occur by chance, we call that statistically significant, right? And it's good when things are statistically significant usually. That's what we're hoping to see. Again, we can never be 100% certain, but it's an effect so large it would rarely occur by chance. And that's kind of what we're looking for. All right. So again, this kind of just wraps up our discussion of experiments for today. All right, there's still some more stuff that we're going to look at next class, specifically kind of setting them up and different techniques to set them up. But this is all vocabulary you want to be familiar with. Blinding, double blinding, statistically significant, placebos, this idea of control groups, random assignment, replication, random assignment versus completely randomized design, kind of knowing the difference between those two, all stuff that you want to be familiar with so that when people are talking about experiments and using this language, you have a framework and a reference point for what's going on there. All right, so that is it for today. Obviously, if you have any questions, just let me know and we'll go from there. All right.